Aha, we've got it. Okay, so this is our second lesson for the precision measurement unit in grade 12 essential math. We're going to talk today about uncertainty. The technical definition is uncertainty is what's called the margin of error of the measurements, usually above or below 1/2 or 0.5 of the precise unit. So for example, a nurse measures a student's temperature at 37 degrees Celsius. Now, chances are she had herself a thermometer. I mean, this probably isn't what the thermometer exactly looked like, but you get the idea, where this is the mercury here and the thermometer, and the mercury went up to, and let's see, 37 degrees Celsius, right? So 38 would have been there, 36 would have been there, something like that, right? So that's what the measurement was. But let's keep in mind that let's assume then that there were no ticks between those numbers. We can't tell. We know it's close to 37. Maybe it was a little hair above it or a little hair below it. So the closest we are kind of estimating with our eyes is that 37 number. So the precision is the smallest unit on the scale here, which is 1 degree Celsius. That means that our uncertainty, it's possible we could be a little higher, it's possible we could be a little lower, but we wouldn't be more than halfway to the next number, or we'd have just rounded it to 38 or 36. So we are uncertain by plus or minus 1/2 degree Celsius. That means that this student's temperature is really somewhere between 36.5 degrees and 37.5 degrees. Between and not including. Again, if it was exactly halfway, we'd have probably rounded it up. Okay? Here's something we were talking about yesterday. Again, the imperial units. Anybody actually know their height in centimeters? Exactly. Even though we're a metric country and we're supposed to be doing things using the metric system, most of us still know our actual height in terms of feet and inches, the old system. I honestly don't know how many centimeters tall I am. To be honest, I don't know how many feet and inches I am either, because I used to be 6'2", but, well, age plays a mean trick on you. I am shrinking. I am not as tall. Gravity is winning the fight. I'm not as tall as I used to be. Oh, what were you wearing when you measured yourself at 5'5"? That's the question. Anyway, my precision, if I say I'm 5'9", is that I am precise to 1 inch, but my uncertainty is I could be off by 1/2 an inch too big or 1/2 an inch too small. So that means that my actual height is somewhere between 5 feet 8 1/2 inches or 5 foot 9 1/2 inches. We talked about a meter stick yesterday. A meter stick has centimeter markings on it, and then there's 10 little ticks between the centimeters. Those are millimeters. So a meter stick is precise to 1 millimeter, so its uncertainty is plus or minus 1/2 a millimeter. Bathroom scale might look like this. It might say, you know, it's one of those kind of windows, right? And you step on it, and then there's the numbers kind of go back and forth. But let's say the bathroom scale is in kilograms, and let's say we'd have 100, and then a tick, and then 101, and then a tick, and then 102. Those ticks represent 1/2 of a kilogram. So the bathroom scale might be precise to 1/2 a kilogram, which means we're uncertain by 1/2 of a half. Quick, what's 1/2 of a half? Exactly, a quarter, plus or minus 0.25 kilograms. Get it? Your uncertainty is always half your precision. It's a pretty simple rule once you get used to it. Okay? Now, what if you have to take your measurements and do some math with them? You have to combine them. There are complicated rules for every type of combination of measurements, whether you could be multiplying, dividing, maybe throwing them into a formula. But here in this course, we're just going to worry about adding and subtracting. If you are adding together 1 liter of fertilizer with 1 liter of water, because you're going to put that on your garden, do some gardening, the measuring device you're using is precise to 0.1 liters. What is the uncertainty of your measuring device? Well, let's see. It's precise to 1/10 of a liter, so that means its uncertainty is 1/2 of 0.1. What is 1/2 of 0.1? And the answer is 0.05. Very good. So I could be 0.05 higher than I think I am. I could be 0.05 lower than I think I am. Now, that's true when I use the device to measure the water and when I measure the fertilizer. Both of those measurements could be off a little bit. So what I do is if I combine them, I say, well, I'm adding 1 liter of water to 1 liter of fertilizer, and the water's measurements could be off by this much, and the fertilizer's measurement could be off by this much. So that means I have to add the uncertainties together as well as the numbers. 1 liter plus 1 liter means that I should have 2 liters, but the uncertainty adds. 0.05 plus 0.05 is 0.1. So that would be the uncertainty of my calculation. So my entire final volume has an uncertainty of 100 milliliters, or 0.1 liters. Sorry, no, 100 milliliters. Okay, so the note, maybe this is our notes, we'll say, add the uncertainties when adding or subtracting measurements. Okay. One more example here. A grocery clerk combines boxes of vegetables with weights of 16.5, 2, and 1.45 kilograms. So box 1 says it's 16.5 kilograms. So my precision is 0.1 kilograms, right? We had a 0.5, so that means we must be able to measure to the nearest 0.1. That means my uncertainty is plus or minus 1/2 of that. So 0.05 of a kilogram. Now the second box just says 2 kilograms. It doesn't have a decimal on it. So I really don't know if, do they mean 2.0 kilograms? I actually kind of don't know that. So I'm just going to say that my precision is basically just 1 kilogram. I don't have any other knowledge that they measured it any more precisely than that. I almost said more accurately than that, but that'd be the wrong word. More precisely than that. Okay, so that means that my uncertainty for this one is 1/2 a kilogram. Now there's somebody usually at this point puts up their hand and asks me the question, what if they did measure it to the nearest 1/10 of a kilogram, it just turned out to be a 0? Well, then you know what you should write? You should write 2.0. That would tell you that you were precise to a 1/10th place. But they don't have that on here. I can't assume that it is. So I don't know that. So I'm just going to say, nope, we don't know that. It doesn't tell us that. Now box 3 has 2 decimal places on it. So its precision, is 0.01 of a kilogram, which means its uncertainty is plus or minus 0.005 of a kilogram. Maybe that box was measured and weighed on a very precise scale, like one of those, electronic scales that they use for measuring very small things, hoping for a high degree of accuracy with a high degree of precision. What is the combined weight of the boxes, including the uncertainty? So, okay, so again, we add them all up. So I'm going to just add them in two things here. So I'm going to say it's 16.5 plus 2 plus 1.45 plus or minus, and then I'm adding the 0.05 to the 0.5 to the 0.005. And that's going to give me, and this is where I think I better double check my answer just to make sure that my notes are right. So using my calculator, 16.5 plus 2 plus 1.45 is 19.95. Did I do that right? 16.5, 2, oh, wait a minute. Oh, hang on. This is 2.8. That's okay. I'm going to assume that's the right number. I'm going to get rid of, can you get rid of that 0.8? There we go. And this box says 1.4, even though the picture says 1.45. I think that they're typos over here. Careful. We got typos. This is supposed to be 1.45. Okay, so I'm going to assume that the picture has the right numbers and that these are typos. Okay? So re-adding this, 16.5 plus 2 plus 1.45 is 19.95 kilograms. Notice I didn't bother putting kilograms in my math and my calculation, but I put it on my final answer. You should do that too, right? If your question had units, your final answer should have units. And then plus or minus, if we add this together, we're actually going to get 0. A 5 in the tens place, a 5 in the hundreds place, and a 5 in the thousands place. Do I have to put kilograms on both of these things, on both the measurement and its uncertainty? You probably should. I've been told when I mark the provincial exam that if people forget to put it here and they just put it at the end, don't take off half a mark for units, and vice versa. If they remember it there but they forget it there, don't take off half a mark. But you never know when those little rules change. Losing half a mark when you know what you're doing is a silly thing to do, so just put units on both the measurement and its uncertainty, and then you know you won't lose half a mark. And okay, calculate the difference between the 16.5 and the 1 point, that's actually again supposed to be a 1.45 kilogram weight. Okay, so the difference, what does difference tell you to do in math? If you're looking for a difference, what operation are you doing? You're doing subtraction, right? So 16.5 minus 1.45 is my measurements, plus or minus, now careful here, here's where people mess this up. What do I do with the uncertainties? I add them. It's like, but I'm subtracting the numbers. Why would I add the uncertainties? Because think about it. The first number could be uncertain by this much. The second number could be uncertain by this much. Put those two things together, that's how uncertain the calculation is. It doesn't matter that the calculation is a subtract. So this is a super easy mistake to make. Okay, so the 16.5 was, let's look back here, had an uncertainty of 0.05. The 1.45 has an uncertainty of 0.005. Make sure you understand that it's adding here, even though it's subtracting there. And then you get a final answer of, let's see, get my calculator happening, 16.5 minus 1.45 is 15.05 kilograms plus or minus 0.055 kilograms. And that's it for notes. Really quickly, I just wanted to point out to you, I was kind of thinking out loud, what kinds of places in the world does accuracy and precision mean the most and is the most important? How about, I asked Google to help me with that. Always nice to Google things when you're not sure. How about this? Lack of precision and accuracy can have severe consequences, potentially leading to loss of life, especially in fields like medicine and manufacturing. If you were imprecise or inaccurate in the equipment you're using to, say, diagnose the size of a tumor, you could lead to a misdiagnosis and inappropriate treatments. If you were doling out medication and you measured, or you had an imprecise or an inaccurate measurement. That could have life-threatening consequences. That's actually one of the leading causes of death in hospitals, is just mistakes when prescribing what should be life-saving or life-maintaining medication. Okay? And how about in the manufacturing field? Something that bears weight, a structural load-bearing beam that's been mismeasured in a house. That could lead to structural issues. Okay? And of course, say that you're in charge of a company's money and you measure things inaccurately, or you're imprecise in the way that you're counting profits and losses. All of these things would have dire consequences in the real world. One last thing, in the world of chemistry, kind of have some pictures here. Here's kind of an interesting comparison. If you've ever in a chemistry lab dealt with these kinds of objects here, that would be a flask on the left, right? That looks to me like it's 200 milliliters, but remember, I can't really tell just looking at it if we're a little bit below it, a little bit above it. I mean, I try, they always tell you in chemistry class, get your eye level with the level of liquid that you're measuring. But I would have to say that my precision here, it counts by, let's see, 150, 175, 200. So its precision is 25 milliliters, which means my uncertainty is plus or minus 12 and a half milliliters. Meanwhile, over here, these are also milliliters, but have you ever tried to measure very small amounts of a liquid, like especially water? Most liquids, especially again liquids like water, have what's called surface tension. It's what allows you to fill up a glass of water a little bit over the rim before it starts spilling. It's because of the surface tension of the water. Here, do a fun experiment. Fill up a glass right to the very top so that it's kind of over the top a little bit, and then dip your finger with a little bit of like dish soap, and then touch the top of the water. Guess what happens? It overflows on you. Okay, because you've broken the surface tension with soap. But anyway, the surface tension, when you're measuring a really small amount of liquid, what do you do? Like, is this line where I take the measurements? Or is it kind of in the middle here? Because see what the water is doing, right? The water is making what's called a meniscus. It's clinging a little bit to the sides of the tube and then shrinking down in the middle. So how do you measure this? You can see the lack of accuracy to the real number if you kind of guess, well, I'm going to guess it's up to here. That looks like the number. So that would be, what would that be? 7.2 milliliters. And then somebody else might go, no, I'm going to use the bottom here and say that this is 6.2, 6.4, 6.6 milliliters. And somebody else might come along and go, no, I'm going to pick the middle, which is, I guess, 7.0 milliliters. So what's my uncertainty this time? My uncertainty is quite a bit bigger than half my precision in this case, because look at how different those three measurements are. They actually do tell you to use the bottom one. That's the way you're supposed to do it in a chemistry lab. Okay? But I'd still say that my precision is how far apart these are, which is 0.2 milliliters, which means my uncertainty is plus or minus half that, 0.1 milliliters. Okay? All right. That's the lesson for now. You can now do all of questions 1 to 8 in this little booklet here. All right. Come on, booklet. There it is. So that's what students are going to work on for the rest of class. All right. Stop the video there.